and thanks to the organizer for inviting me. So I'll speak on this title, Locus of non-very stable bundles and its geometry. So let me start with very basic definitions. So I'll fix some notations here. So X is a smooth projective curve. For complex numbers, K is the cotangent bundle. On X. So I'll denote MRD with that moduli space semi-stable of isomorphism classes. Classes of semi-stable bundles. Rank R and degree D. So let E be a vector bundle. On X. Then in Higgs field, so Higgs field is a morphism from E to E tensor K. It's a bundle morphism. So we say phi is nilpotent. So we say phi is nilpotent if there exist R such a phi power n. So here phi is this composition map. So we have a map E tensor K. This is P cross identity. So this composition map is phi R. So we say that phi is nilpotent if this composition map is 0. And we say that pair is a nilpotent pair. This pair is called nilpotent. If phi is nilpotent. So we'll assume from now on we'll assume E is stable vector bundle. That means so E is a point in MRD, stable vector bundle. Or if we restrict ourselves on this case when R and D are co-prime, and then stable, semi-stable are same. So in that case, we denote MR is that moduli space. So this is moduli space of stable vector bundles. Bundles of fixed determinant. Of odd degree. Of degree D, such that R and D is co-prime. So in this case, the Higgs fields, if E is a point here in MR, Then the Higgs fields can be identified as the points of the cotangent space T star of MR at that point. So the cotangent space can be identified with the sections of edge of end nodding. Here end node means it's a trace-free endomorphism. So phi belongs to this is an element here. That means phi is a morphism from E to E tensor K with trace of phi is equal to 0. So we say that a stable vector bundle is very stable. Definition. Stable vector bundle is very stable if he admits no non-zero nilpotent Higgs field. So it is always true that if E is stable, then always true that there exists a nilpotent Higgs field. So in particular, phi is 0. If we take phi equal to 0, then this is 0 nilpotent Higgs field. But a stable bundle is said to be very stable if admits no non-zero nilpotent Higgs fields. That means if phi is an element, so the phi is an element from E to E tensor K, such that phi to the power r is equal to 0, this implies phi is equal to 0. Then we say that E is a very stable bundle. Now, it is known that, or it is not difficult to see also, that this locus of very stable bundles forms an open subset of MR. And the non-emptiness, Lomov proved that this is also proved the non-emptiness, the existence of such bundles. So if this locus, so this says that it is non-empty open subset, and this says that it is non-empty, so it is a non-empty open dense subset. So locus of very stable bundles forms an open dense subset. So now question is, what is the complement? Complement we call non-very stable bundles. So we denote MV is that complement of so this is I say that this is a locus of non-very stable bundles. And so since this is open subset, non-open dense subset, so this is a closed subset, a proper closed subset. And so what can you say about this closed subset, the dimension, etc.? So Drinfeld claims that this MV is of codimension 1, is an equidimensional variety. Dimensional subvariety, subset, closed subset of codimension 1. this proof of this statement is missing. So there is no proof of this statement. So that's why I try to give a proof. So in this lecture, I will give a sketch of this proof of this theorem for rank 2 case. So the theorem is, so the locus of non-very stable bundles vector bundles of rank 2 and of a fixed determinant delta of degree 1, where delta is a line bundle of degree 1 is of co-dimension 1. So I will give a sketch of this theorem, but before that, I say a few words, at least something about the geometry of these stable bundles. So to say that, so I will start with some basic geometry on quadrics. So I'll start with the geometry of quadrics. Geometry of quadrics, and then I'll relate this geometry with hyperelliptic curve of genus G. So on theorem, so they are arbitrary smooth projective curve, but I will for the geometry, when I will explain the geometry of this non-very stable locus, then I will restrict myself on hyperelliptic curve. So geometry, so let Q be a smooth quadric of dimension m, then Q doesn't contain, Q contains a linear subspace of dimension at most m over 2. Furthermore, if m is equal to 2g plus 1, then G and Q contains a family two-dimensional linear subspaces family of dimension G of linear subspaces of dimension G. Number 2, if m is equal to 2g, then Q contains two distinct irreducible components, component of G into two-dimensional family of G planes. So number 3, in case 2, for every G minus 1 planes, there exist exactly 2 G planes containing it and contained in Q, and they lie in the defined component. That means if Q is a smooth quadric of dimension 2G, then and we are given a linear subspace, say G minus 1 planes. So lambda is a G minus 1 planes. Then consider all those G planes contained in Q. Q has 2 irreducible components, 2 components say sigma 1 and sigma 2. And this saying that, and there exist exactly two G planes, say lambda 1 and lambda 2, such that lambda contained in both lambda I equal to 1 to 2, and lambda I belongs to sigma I. They are distinct components. So using that result, we can describe the geometry of hyperelliptic curves. So consider let consider V the vector space V of dimension 2G plus. Then and choose 2 coordinates. So let Q1 and Q2 are to be 2 smooth quadrics on PV. So in this case, if we assume that Q1 and Q2 are smooth and the intersection is also smooth of codimension 2 exactly, then we can diagonalize both Q1 and Q2. So without loss of generality, we can assume, if we want, that Q1 is equal to sigma of x square and Q2 is equal to sigma of omega I x square, where omega I is not equal to omega g. So in this situation, so we'll define a pencil of quadrics. So pencil of quadrics means a family of quadrics in P1P is a subset in S to V star. So this is defined by, so we can think this family pencil of quadrics as the set of all quadrics given by this lambda 2 q2 where lambda 1 lambda 2 belongs to p1. So this is a pencil of quadrics. These are all quadrics passing through the intersection p1 intersection p2. So now we defined define GNP is set of all Q. I'll explain what is Q and E. Such that just write Q restriction lambda is equal to 0. So this is a subset of P1P cross Grassmannian of G plus 1G. So what is Q? Q is the associated bilinear form corresponding to Q. If you capital Q is a point here, so so Q is the associated. So Q is a point, capital Q is a point, then the corresponding bilinear form will denote by Q, small q. So then clearly there is a projection map from this variety to P1. Just Q lambda goes to Q, is associated Q. So what is the fiber of this map? So Q is an element of P1. Then the fiber, say this is pi, or projection map P1. Then P1 inverse Q is nothing but set all G planes contained in Q, right? So this is so variety of G planes contained in Q. Now, by that theorem says that this set has two distinct components. Right? That 2 says that if M is equal to 2G, then Q contains two distinct irreducible component of this dimension. So next theorem says that this map P1 to P1 has a Stein factorization so like this P1 to P1 and this is so since it is Stein's factorization, so X, what is X? X is a curve. X is a smooth curve. And what is the fiber of this map? Is just a number of the fiber of this is that irreducible components of this image of inverse image of this. So if you take an element here Q, then fiber this then phi inverse Q is that irreducible components. Irreducible components of P1 inverse Q. But what is P1 inverse Q? Is that variety of all G planes. So it has two components. So the cardinality of this fiber is 2. So it's a 2-1 map, and that ramified this map is ramified exactly at those points where this quadrics in that pencil are singular. So this X is a, so what we have, so this X is a hyperelliptic curve. And we can easily calculate that this genus of G, genus of the curve is exactly G. The singular locus of this family of, in this pencil, the singular locus are exactly 2G plus 2 points. And so this map is ramified exactly at 2G plus 2 points. And so we can calculate that genus of this curve is equal to G. And so from this theorem, we can think the points of X. So points of X can be thought as pairs Q sigma. Where Q is a quadric in, just like Q is an element of P1, P, and sigma is an irreducible component of G planes. So now it is known, this the known fact, Desale-Ramana, that the Jacobian J of X is isomorphic to variety of lines. In variety of G minus 1 planes and Q1 intersection Q. So now we will restrict ourselves for the case when G is equal to 2. So now fix. So now, so consider the case G is equal to 2. So in this case, X is a curve of genus. So genus of X is 2. And the Jacobian of that curve is set of lines in Q1 intersection Q2. So now what we will do is to, given any point on X, we will define an involution on the Jacobian. So how we will define that geometrically? So take a point Q sigma. This is an element of X. So as I mentioned there, any point of X can be identified with this pair. So this will give a point on X. So I'll define an involution on Jx how. So and take L is a point of Jx. So L is a line here. And then by this result, that any G minus 1 planes, there exist exactly 2 G planes. And they belongs to the opposite component. So for given L, so there exists unique plane lambda belongs to sigma containing now what we got is this is a unique plane belongs to sigma which contains lambda. So if we restrict intersects lambda, so lambda intersection q prime for any q prime belongs to p1 p distinct from minus q. So since L is a is contained in there because L is in the intersection. So L is a point here. So it's lie in the intersection. So this contains L and this also contains L. The intersection contains L. So it is a conic. So it is a pair of lines. Because L is already there, so intersection will be L dot L prime. So just defined this involution. Just taking L takes L to L prime. So if we pass through the question, then we will get a Kumar surface. So we get a Kumar surface for each. So for each, we get a Kumar surface. What are the singular locus? Singular locus are exactly all those L such that this corresponding lambda intersects other quadrics in two line square. So if L belongs to Jx such that I Q sigma L is equal to L, that means this is perfect square, not pair of lines, it is a line square. Then this is a singular point, then L is a singular point. Singular point of this. So now we introduce some definition. A line, a point, or a line in Q1 intersection Q2 is called special if a line L, and the intersection is called special if there exists if L is a singular point of a Kumar surface. For some point K sigma. And next, the point P in the intersection is called special point special if P belongs to some special line. So one more alternative description which actually follows from this definition, that so if P is a point in Q1 intersection Q2, then we can define P perp. P perp is that P1 P perp with respect to Q1 intersection P perp with respect to Q2. So these are quadrics, so you can consider the bilinear form associated to that and take the P perp with respect to that quadric and this, take the intersection. So since this is smooth quadric, so this intersection has dimension, the dimension of P perp, vector space dimension is 4. So if we take the projective space, it is a P3. It is a P3. Now, if we intersect this P3 with those Q1 and Q2, then what we will get? This is a cone. This picture is like a cone with a vertex. This. So this is a cone with base intersection of two quadrics. So it contains these four lines always, generally. So we say P is a, so we take the delta we defined, all those P in Q1 intersection Q2, such that P perp contains less than four lines. So the general situation is like this, but in some particular point, this intersection might be 3, not 4. In that case, it will contain 3 lines. So delta is the set of all points such that this corresponding P perp contains only less than 4 lines. Then from this definition, one can easily prove that delta is nothing but the set of all special points. Okay. So it is not hard to see that delta is equal to the set of special points. And it is classically known, the surface delta is already well studied, classically it is known, and classically known that delta is a smooth surface of degree 32. So why I am interested on this surface? So I started with defining the non-very stable bundles, and what I stated a theorem that the locus of non-very stable bundles is codimension 1. And for genus 2 case, so since for genus 2 case, for G equal to 2, we know that M2 is isomorphic to Q1 intersection Q2. This is by Riemann, Narasimhan. So they proved that for genus 2 case, this modular space is isomorphic to intersection of two quadrics in P5. So so the modular space, so the locus of non-very stable bundles is a codimension 1 subset here. So what is that? So that is actually this delta. So next theorem, what I prove that M2V is isomorphic to the set of all non-very stable bundles. Sorry, non-very stable bundles is isomorphic to delta, this surface. So if I get time, then I will give a sketch of this proof. So let me come back to that proof of that theorem. So that theorem says that this M2V is of codimension. We'll give a sketch of this proof. Genus 2 case. This one is genus 2 case, but this is general, arbitrary genus. This one is arbitrary genus, but rank 2. But this case, this isomorphism only for genus 2 case. And this is for arbitrary genus. So first before going to proof, I state a lemma. So I just state a lemma. A stable vector bundle E admits a non-zero nilpotent Higgs field if and only if E contains a line subbundle xi inverse such that is not of K tensor 2 tensor delta minus 1 is 9. So I have already fixed this. This is fixed determinant of delta. I have already mentioned. So this is equal to non-zero. So if we assume this lemma, then what it says that now degree of this line bundle degree of K tensor suppose degree of assume let degree of xi is equal to d. Delta I have already fixed. So I have said that M R, this is the modular space of rank R and determinant delta. We fixed determinant delta, but such that the degree of delta and R are co-prime. So degree of this is equal to 2g minus 2 minus 2d plus minus. So to have this line bundle has section is always must be greater than or equal to 1. So it is odd degree. It must be greater than or equal to 1. So this implies that d is greater than or equal to minus g minus 2. So, and since on the other hand, since E is stable, since E is stable of degree 1, since I have already fixed the delta, since E is stable of degree, so since E is stable, the degree of xi is less than or equal to 0. So we'll write this way. So this MV can be written as union of yi I equal to 0 to z minus 2. So what is yi? So yi is the set of all E belongs to MV, M, M2, such that E contains a line subbundle of degree minus I. This I have defined since by this result that since it is a non-vegetable bundle, so it always contains a line subbundle of this with this property, and with this property it says that degree is greater than or equal to this and at least 0. So in between, sorry, degree of E is 1. I have fixed already. 1. Delta is a line bundle of degree 1. This degree of xi. Now, so if now if E belongs to some yi, then what it says that there exists a line bundle xi such that degree of xi is equal to I, and xi minus 1 is a subset of E. And this property says that H naught of k tensor xi minus 2 tensor delta minus 1 is not equal to 0. This implies that this degree is 2g minus 2, and this is minus 2y minus 1. This is greater than equal to 1. So this implies, sorry. Yeah, so now, so if we got 2g minus, degree of this line bundle is 2g minus 2I minus 3. So degree of this line bundle, this is degree of k tensor minus 2 tensor minus 1. Now to say that this bundle has a section, so that means this in this line bundle sits inside the below the loci. So this condition gives that k tensor 2 tensor delta minus 1 belongs to W naught 2g minus 2y minus 3. So at least one section. But but Abel's theorem says that x 2g minus 2y. This is a symmetric product. 2g minus 2y minus 3 is a symmetric product of x to this map P-card group of 2g minus 2y minus 3. This map gives an isomorphism between open subset of this, and so gives an isomorphism between an open subset of x 2g minus 2y minus 3 and 2y minus 3 minus. So this says that the set of all line bundles satisfies these conditions has dimension 2g minus 2y minus 3. So I says that is not of k tensor 2 minus not equal to 0 has dimension 2g minus 2y minus 3. So now choose a point. So let if 2g minus, sorry, has dimension 2g minus 2y minus 3 if 2g minus 2y minus 3 is less than equal to g, or which is same as I is greater than equal to g minus 3 over 2, and is equal to g if 2g minus 2y minus 3 is greater than g. Oh, sorry, this is less than equal to I is greater than equal to g minus 3 over 2. So choose an I. So let I be such that I belongs to some integers, I with the integer such that I is less than g minus 3. So now consider, so and choose and take a line bundle xi of degree I. Then consider this extension. So the extension classes can be is classified by this phase h1 of xi minus 2 tensor delta minus 1. And the two extension classes are give same isomorphism bundles if they are scalar multiple of them. So this gives a family of vector bundles parameterized by this. And the dimension of this we can calculate. It is minus 2i minus 1 plus 1 minus 3 minus of this minus 1. So this is equal to g plus 2i minus 1. Now we will prove the following result. Fact 1. So one that there exists an non-trivial extension that associated bundle is stable. So we considered arbitrary extension of these forms, and we proved that in this space there exists at least one point which gives a stable bundle. So therefore, we will get an open subset. So if we assume this 1, then 1 implies there exists open subset ui inside this P of h1 psi minus 2 tensor delta minus 1, consisting only table bundles. So by universal property of moduli, there is a map from this to M. Now, consider the Vi is the set of all vector bundles belongs to Ui, such that E doesn't contain any line subbundle of degree larger than minus I. So this is a subset of Ui, and we can prove that this is a non-empty subset of Vi. And this is not difficult to see. Then Vi is a non-empty open subset. And next fact 2, these are all we have to prove. We know the. So then we prove that this, if we consider, so therefore, if we restrict that map, then we'll get a map from the just restriction of this map of Vi. So Vi is open here. So in this case, we can prove that this map is injective. If we restrict that map on that's open subset, then this is injective. So therefore, for each xi, we'll get a family of vector bundles of dimension g minus 2i plus minus 1, g plus 2i minus 1. So dimension, since dimension of Vi is equal to 2g plus 2i minus 1, sorry, g plus 2i minus 1, and xi varies over a subvariety over a subset of dimension 2g plus, sorry, what is the dimension? 2g minus 2i, 2g minus 2i minus 3, 2i minus 3. So dimension of yi is equal to g plus 2i minus 1 plus 2g minus 2i minus 3, basically 3g minus 4. And we know the modular space of stable vector bundles has dimension 3g minus 3 if we fix the determinant. So it is a codimension 1. So that proves that theorem. Okay, since I don't have time, only 3 minutes, I'll stop here. No, I don't know.